Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you for coming. This is wonderful. You're here at lunchtime. Appreciate that. I also have very happy to introduce to you Jennifer. Professor Expert is actually a professor at Princeton University, where she also got her bachelor's from, and then she got a PhD from Michigan, University of Michigan. She is unique in the sense that she is in academia now and she's teaching, but she has spent a substantial amount of time in industry. So she has been at AT&T for about 8.5 to 9 years before deciding to go to academia. So she has a good sense of the priorities of research labs and as well as academia. And so in fact, the fact that our students are so hard commodities for us to get is a good thing. But she's visiting us for a few weeks, and as part of that, I sort of gently suggested that maybe she should tell us a little bit about the things that she's been working on. She's very accomplished. She was chair of SIGCOMM for 4 years. She also got some awards, Grace Hopper Awards, etc. But you can read that in the bio. So without further ado, Jennifer.
Thank you. Thanks. It's been a real pleasure to be here the past few weeks. And actually, Victor's intro was perfect because this particular piece of work was born out of some issues that we'd grappled with when I was at AT&T. And I had been wondering about them for a long time. And I hooked up at Princeton with Mung Chiang, who's an optimization theory guy in our electrical engineering department. And this work is done in conjunction with him, looking at some theoretical techniques that he has for creating network protocols that are implicitly solutions to optimization problems. And so what I want to talk about first, though, is in the networking research community the past few years, there's been a kind of buzzword that if you're in the networking community, you've heard more times than you can count about clean slate network architecture. And I wanted to dwell on this for a moment because this talk is really about that topic. So what does that mean? So network architecture is more than tuning a particular protocol on the internet or tweaking its performance. It's really about the basic definition and placement of function. What things should be done by the routers and switches, what should be done by the end hosts, what should be done by automated management systems or human operators. So I want to, in this talk, revisit the traditional definition and placement of function for a particular network task that I'm going to call traffic management. So that's what I mean by network architecture. So what does clean slate network architecture mean? Well, it means thinking about this problem without the constraints of today's artifacts. So what does that mean? It doesn't mean ignoring the speed of light or cost of memory, but it means not worrying about some niggly little detail in some existing IETF standard that often, when I was at AT&T, would constrain the way I was allowed to think about a problem if I wanted it to be used in practice. So why is that useful? Well, part of the goal is to build us a stronger intellectual foundation for designing, deploying, and managing networks by being able to think from scratch about how protocols should be designed and used. And there's some belief that to make the internet better, we may even have to change the internet architecture in somewhat fundamental ways. And so there's still an open question about whether this is more than just an intellectual exercise, but might in some cases actually help us make the internet better in a more practical way. So that's all well and good, and that people have been talking about this for a while, but one of the things that I found perplexing about it is it's not really clear how one does this. How does one do? Okay, I decided I want to be a clean slate network architect. What do I do? What do I do when I start my day? And so I've been talking a lot with Mung Chiang about what to do, and he and a number of others in his area, Frank Kelly, Stephen Lowe, et cetera, have a really interesting body of techniques for viewing distributed algorithms, protocols, as implicit solutions to optimization problems. And these are algorithms that, in fact, the math tells us how to derive. And so you can view this talk really two ways, and I'm going to view it primarily the first way, which is I'm going to walk you through the design process that we went through in solving a problem that I had worked on from a much more bottom-up perspective for a number of years when I was at AT&T. If you're someone that likes the journey more than the outcome, this is a talk for you. If you really are interested in the outcome, I will get to that, but it's going to be somewhat superficially treated because I'm really trying to walk you more through a design process than I am preoccupied with the particular outcome we get. So we're going to look at traffic management. So what do I mean by that? I mean, what is it that allows us to compute for each path through the network between every pair of nodes, what bit rate I'm going to send traffic on that path. And so I define it that way because it encompasses most of the major resource allocation issues that the networking community thinks about. Routing, the computing of the paths, congestion control, the adapting of the sending rates of the sources, traffic engineering, the tuning of routing by the management systems to decide which paths that traffic should go on. And so what I'm going to talk about is going to encompass those three topics, but it's going to revisit what division of labor we should have between the routers, the end hosts, and the network operators in solving that problem. So why do I want to look at this? Well, it's a pretty broad topic that is pretty basic in networking. But frankly, more importantly, it's at least something I think there's some hope in getting traction on mathematically. And so it seemed like a good place for us to start our activity. And why can we get traction on this mathematically? Well, there's been really lovely work by Stephen Lowe and Frank Kelly on reverse engineering TCP congestion control that shows it's implicitly maximizing user utility summed over all the users in the internet. People have recently made some great progress doing forward engineering using these same techniques, designing new variants of TCP like TCP fast in Stephen Lowe's group. And also, people have used optimization theory to tune the existing protocols, the existing routing protocols. And in fact, work I was involved in at AT&T took this approach. We assume the protocols are given, but they offer us knobs that we can use optimization theory to tune. So, important problem, pretty broad in networking, and some at least hope that we'll make progress studying it mathematically. And yet a problem that's not solved enough that it's a waste of time for us to work on it. It's still an area where there's not really a good holistic view. And part of the reason for that is traffic management and the internet we arrived at it fairly in an ad hoc fashion, as is true for most protocols in the internet. So what do we do today? Well, the routers, they talk to one another and they compute paths through the network dynamically based on the current topology. The end hosts run congestion control algorithms that increase and decrease their sending rates in response to congestion on the paths they're using. And the network administrator is sitting on high, or automated systems acting in his behalf, to tinker under the hood with the configuration of the individual routers to coax them into computing different paths so that when the users do their thing, the traffic flows more effectively through the network. And as I mentioned before, this evolved really organically over time without much conscious design. So why is that? Well, you always needed the routers to compute paths. That's been pretty basic from the very beginning. Congestion control was added to the internet in the late 80s when there were starting to be fears of congestion collapse as the internet became more popular. And traffic engineering became important in the sort of early to mid 90s when the internet became commercial and ISPs started to see significant growth in internet traffic with the emergence of the web and had commercial motivations to have performance be good and the links to be used efficiently. So these three things are running completely independently. The vendors and the IETF dictate the routing protocols, the IETF and the end hosts dictate congestion control, and the network administrators in each ISP in the internet dictate the traffic engineering. So as you might expect, this works. I mean, we all are using the internet, although probably some of you right now, in fact. But it doesn't necessarily work well. And so what's wrong with that? Well, the interaction between these protocols and practices are not captured. Congestion control assumes routing isn't changing. Traffic engineering assumes the offered load is inelastic, when in fact we know it's fluctuating in response to congestion. Traffic engineering itself, given today's routing protocols, is complicated. It's an NP-hard problem to tune the link weights that the routers use to compute shortest paths, to do traffic engineering. And every time an adjustment is made in the network, the routers spend a bit of time talking amongst themselves, leading to transient disruptions. So people tend not to adapt the routing of the traffic on all that fine a timescale out of fear of causing transient disruptions. And finally, even though the topologies have multiple paths, they're used only in very primitive ways. Most of the internet protocols make very limited, at best equal cost multipath use of multiple paths. So in light of all these things, the question that Mung and I were curious about is, if you could start over, knowing all these things we know now, what would you do differently? And that's essentially what this talk is about. And I'm going to be fairly deliberative about process here, because the process that we went through for designing the protocol is really, I think, the part that's more interesting than the protocol itself. So first thing we're going to do is formulate the problem we think the protocol should be solving. Sounds basic, but you'd be amazed how many protocols on the internet, we still don't know what problem they're actually trying to solve, and we're not even sure they solve them. So we're going to formulate a problem, and I'm going to draw inspiration from today's traffic engineering practices and congestion control protocols. I'm going to use Mung's magic optimization theory stuff to derive distributed algorithms that are provably stable and optimal realizations of that optimization problem. So that's where Mung is very happy, but I'm not, because the theory only tells us that the thing is stable and optimal, not how quickly it's going to converge or how sensitive the protocol is to tunable parameters. So I'm not happy. So we're going to run a bunch of simulations to understand how well these, in fact, 4 different protocols that all are provably stable and optimal, but some are better than others in practice. Simulations will tell us that some are better than others, and in fact, we don't like any of them. but each of them have some ingredients that we'd like to cherry pick. And so I'm going to use a little bit of human intuition to pull the best features of each of these protocols and design a new protocol that is not provably stable or optimal, or it is only provably stable and optimal under a narrower set of conditions. So it's not an optimization decomposition, although we can at least say some things about it. But it actually is much simpler and much better in practice. So when you watch a movie and it says it was inspired by real events, this is the place in the talk where that happens, where the theory inspired us to do what we did, but we start to deviate from the theory. Finally, even that algorithm is extremely abstract. Traffic is fluid, feedback delays are constant. So we're going to translate that into a packet-based protocol that we can actually simulate in detail in a packet-level simulator and make sure that the properties of the protocol that we think we've inherited from the theory are still there when it becomes a real protocol. That's the story of the talk. So feel free, by the way, to interrupt me anytime if you have questions. Okay, so the most important thing that we're going to do is the beginning, which is what problem do we want this protocol to solve? And so I'm going to just take a moment to look at what TCP does and what network operators do to get inspiration for what things we'd like the combined system to do. So TCP, there are a bunch of source destination pairs in the internet. I'm going to index them by I. And they implicitly solve, as shown by Frank Kelly and Stephen Lowe and others, a utility maximization problem. So essentially, it solves in a distributive fashion, aggregating the aggregate utility, subject to the fact that the routes combined with the traffic that goes on those routes has to make sure no links are above capacity. And the variable is the sending rate that the source is sending its traffic at. So all the different variants of TCP have a slightly different definition of utility, but they all have the same basic property, that as you send more, you're happier, but they're diminishing returns. And there are a whole bunch of families of alpha fairness definitions that come from economics. There's sort of log utility functions. All the different major TCP variants have been traced back to some definition of a utility function that looks like this. And essentially what that utility function represents then is some notion of user satisfaction, where more is better, but it's really important to get more when you don't have much to begin with. And in fact, that these applications we run on the internet are elastic, that if we can take advantage of the extra bandwidth when it's available, but we can still function when it's not. Okay, so that's the problem TCP solves. Yeah.
So are you still looking at throughput as the metric that you care about in some sense?
Yeah, that's a great question, yes. Okay. And in fact, in a separate work that we did as a follow-on to this, we looked at delay instead and tried to have a minimization of aggregate delay. And we end up with a different protocol, but it goes through exactly the same design process to get at that protocol.
Yeah, the question is, you have a mix of users, right? How does that?
Yeah, and then we looked at what do you do if you have a weighted sum? And essentially the same theory can be used to help us solve that problem too. So I'll touch on that real briefly at the end, but you could view this as just an example, and you're totally right. We chose throughput here, and if you didn't, you'd end up with a completely different protocol with similar structure, but the details would be totally different. Yeah. Any other questions? So that's the congestion control piece. So what do network operators do today? Well, they look at their network, and they don't want the links to be congested. And so they're trying to minimize some sum of congestion over all the links. And typically that congestion function looks something like a queuing delay formula, where they're pretty happy as long as the links are below 30, 40, 50% utilized, and get increasingly unhappy when the link approaches capacity or exceeds it. And they need to do that in such a way that the link utilization is the sum of all the traffic imposed on routes that traverse that link divided by the capacity. So unlike in the previous problem where the source rate was our variable, here it's a given. Because the traffic has been measured, it's the offered traffic as far as this network knows. And in fact, the routing is the variable. Whereas in the other problem, the reverse was true. Okay, so the goal here then is to have a cost function that's a penalty for approaching link capacity. So why do we care about this? Because the network is not terribly robust when its links are operating very near capacity. A small burst of arrival of new traffic from a new source will cause the network to go over a cliff and drop tons of packets on the floor. And so while the user is driving the network into being as heavily loaded as possible by sending as much as he can, the network operator is saying, whoa, and holding back, trying to keep the links from being overfull. Yeah?
If this is the same C1 as on the previous slide, then it means that U1 is at most 1, right?
You want what? I'm sorry?
If this is the same C1 or CL as on the previous slide, then U1 is at most 1, right?
In theory, yes, but if your routing is mismatched to the traffic, you might have a utilization over capacity.
So could you just explain quickly what is the meaning of CL or C1?
So CL is the capacity of link L, And RLI XI is the load put on link L by just that one flow that's traversing link L. And then I'm going to sum up over all flows that traverse link L. And in theory, it can't be above 100%, but I'm going to allow it to be over 100%. You can sort of think of the parts above 100% and it's getting dropped on the floor because the link can't carry them. And that's why I allowed this function to shoot up to near infinity, but to still have a meaning when it's in excess of 1.
So I index is a pair and L index is a pair.
So L is a link, and every flow I will traverse a sequence of links that are, if RLI is 1, that link is on the path, and if it's 0, that link isn't on the path.
So only you do not sum over all I, but only those related to L.
Yeah, exactly. But you can think of RLI as 0 for the links that don't that are not on the path traversed by L. By I. Exactly. And if it's multipath, that RLI might be 50-50, on the two paths, for example, that carry traffic for flow I. Yeah. So that's the problem that the operator is solving, and this essentially avoids bottlenecks in the network. Yeah.
They are also optimizing for latency and a couple other factors, right? Or is that cost? So
that's true. We don't capture that here, but you're right. That kind of implicitly gets captured in the sense that if you take really circuitous paths, it imposes load on so many links that you tend to be biased towards paths that don't have high delay. But you're right, we're not explicitly capturing that here. But you could imagine extending a problem to have it.
The first order and then the second order is latency, and then the third order might be cost or vice versa. So.
Right. So here we're just capturing the congestion piece, but you're right that delay will matter too. Yeah.
Is there an implicit notion of burstiness here that essentially you can buffer things up if that beautiful essentially exceeds 1, or in terms of looking at the average versus a burstiness here?
Right. So a limitation of the theory is that we're thinking really of everything as a fluid, so that there isn't burstiness. But you could view indirectly that we're capturing the burstiness by caring about this, because in theory there's no reason we couldn't run the link almost at 100% utilization, but our reluctance to do so is based on our intuition that that's going to be bad when traffic is bursty. So the theory doesn't capture it, but we're including this piece in the problem because we're worried about it. Yeah. And these are exactly the issues that we're going to end up with a protocol that we think we can say something about, but in practice we don't really know how it performs when the traffic is bursty. We just have a hunch that we've designed it with those constraints in mind, and when we simulate, we'll capture the actual burstiness of the traffic. Yeah, good question. So then what do we do? So essentially what we do is we combine these two objectives together. We say we want to maximize user utility minus the congestion penalty that we're imposing on the network with some weight between the two. So one way to think about that is we're trying to balance the goals of the end hosts to maximize throughput, which tends to push the network towards being bottlenecked, while being aware of the network operator's desire to minimize queuing delay and avoid congestion in the network. And if W is 0, we're essentially doing very much the same objective function that TCP has. If W is very large, we're essentially just doing traffic engineering and being incredibly conservative about what traffic we even let in the network in the first place. And we'll see that having W equal to 0 is a fairly fragile place to be, but having W just a tiny bit larger than 0 is actually the sweet spot for us, where we almost maximize throughput without making the network quite so fragile as it would be if that was all we cared about. So I'll come back to this penalty weight again a little later when we do the numerical experiments. Okay, so what do? So now we've got this optimization problem that we formulated, and now we need to find a distributed protocol that solves that problem. So we're going to use the mathematical techniques that Mung Chiang and his brethren have come up with. But one problem we're going to run into is there's a sort of watershed in the optimization community about problems that are convex and problems that aren't. And we don't really know how to deal with the ones that aren't terribly well. And so the first thing I'm going to do is I'm going to force the network to make the problem that Mung solves be convex. So this is the dynamic Mung and I have. I tell him a problem. He says, that problem's really hard. I'm going to work on it. It's cool. And I'm like, no, it's hard. That's my problem. I'm going to make it easy. And so my job is to make Mung's life easy, and his is to make mine hard. So convex problems are great because there's a local minimum. That's also the global minimum. You can use gradient descent techniques to find it, and those are amenable to distributed implementation. Non-convex problems don't have that property. You can easily get stuck in a local minima, and so you have a hard time making a distributed algorithm that'll find the global minimum like that. Okay, so we want to have convex problems. We know how to handle them, and we know how to derive distributed solutions, in fact, that are computationally simple that provably converge. Okay, so why is our problem not convex the way I've talked about it so far? Well, the main reason is because I'm assuming single path routing, or at least I haven't stated what those routes are. So going back to the question that you asked a moment ago, what is this R? It's the set of links that flow I traverses in the network, and if that's restricted in some way, like 100% of the traffic has to go on one path or 100% on the other, as would be the case with today's single path routing, Or even if I use ECMP, that I require only even divisions of 1 over n across the paths, I don't have a convex problem because I have these kind of weird constraints imposed by the way I can split over multiple paths. So I'm going to rephrase my problem in terms of multipath routing, where I'm going to assume now that I have a set of paths between every ingress-egress pair. And this gets back, I think, a question you asked about, somebody asked about delay. Yeah, it was you. So I'm going to pick these paths smartly so that I pick paths that don't have high delay. Okay, so I'm going to introduce a little practical stuff under the hood here to pick not all possible exponential set of paths, but just a few that are reasonably disjoint and don't have really huge delay. And then I'm going to now say the problem I'm actually solving is to maximize utility summed over the utility I get across all the aggregate rate that I'm sending, where that rate is split over multiple paths, such that the sum of the link loads, again, the links loads individually can't be more than their capacity. So essentially, I've just converted what was originally a single sending rate question to now a multi-rate sending problem of how much I'm going to send on each of multiple paths. And I'm going to assume I can do this in any division, completely arbitrarily fine-grained. Okay. It could be 50-50, it could be 49-51 if I need it to be. And that's possible today using a variety of techniques that help multiple packets of the same flow stay on the same path, using hashing techniques, for example, to do pseudo-random splitting rather than truly arbitrary weighted random splitting. Yeah?
So to get the convexity, do you have to pick the paths carefully?
No, the main thing I need is the splitting. Yeah, really good question. I actually don't really care. The main thing I'm getting out of how I pick the paths is because I'm not choosing to represent every possible path on the graph, I'm stepping away from optimality, right? Because I originally was allowing any path potentially to be used, but now I'm essentially not allowing the path 987321546, and it could have been that the optimal solution would have used it, and I'm not. So it's more that I need to pick a reasonable set of paths that the optimal solution doesn't lie far away from what I'm letting get expressed here. But the good thing is picking like the k-shortest paths or the k-shortest paths that are at least somewhat disjoint from one another seems to work pretty well. Most of the graphs I've looked at, and I know data centers probably don't look like this, but don't have so much path diversity that that's hard to do. In a data center, that might not actually be the case.
So you're saying you're varying the rate along each of the paths, so one path might carry traffic at a greater rate than another?
Exactly. Yeah, and so you could think of that 2 ways. You could think that the component that's sitting here, which could be an end host or an edge switch, either is computing those rates and sending at them, or is computing an aggregate rate so that the host is told, send at whatever the sum turns out to be, and the network is just doing proportional splitting based on the relative ratio between those weights. Or you could think of a single component doing both those functions. Yeah. But the user utility is defined just as in terms of the aggregate, because it's sort of oblivious to which one it's using.
About the intuition behind what makes it convex, because I didn't get that, because in one case you had a binary variable of just choosing the path, and now you're saying, well, instead of it being integer, I'm going to use some 0.2, 0.8 split, right?
Right, so one way to think about it is the way I formulated the problem here, before I changed the problem, I was requiring this to be 1, 0, 0, or 0, 1, 0, or 0, 0, 1. And so I actually have discontinuities that are introduced by that constraint, which essentially leave me with situations that are a bit like this picture on the right. Now I've got continuity, so I can make progress by just imperceptibly shifting a portion of traffic from one path to another. And all the solutions in between are feasible ones in my model. Whereas in the earlier model, I was forcing things to be discontinuous. I could only have integer solutions in a sense before I made this change.
So just the fact that you're moving from integer to just a linear program solution is what makes it.
Exactly. Yeah, exactly. So it's not the set of paths. It's purely the fact that I now can have a continuous solution rather than a discrete one.
It's basically went from essentially an integer linear program to the standard. Yeah.
Exactly. So essentially, I'm in the realm of multi-commodity flow now. Right. Yeah, exactly. It's the same reason MPLS can achieve optimal traffic engineering, but OSPF can't. Right? Because the ability to do arbitrary splitting is the key that's keeping the optimization problem from being tractable and optimal.
But then you don't need to find a number of paths or
I'm only restricting myself to that for computational simplicity, and in the sense that I don't really want this node in practice to have to deal with exponential number of paths, because I'm going to keep state in the end host or the router in proportion to that. So it's purely the theory doesn't really require me to be so restrictive. It's more that I just think in practice it's not realistic to enumerate all the paths, and I also don't think it helps much beyond a certain point. But there's no reason I couldn't conceivably do that. It just doesn't make practical sense. Yeah.
If you were to fix paths up front, even fixing one path will still work. I mean, what you mean by single path routing is letting the problem choose the route. That's what's not Convex.
Even in this setting, if I pick 3 routes and I say pick one of the 3, I'm still going to have a problem.
Yeah. But if you just pick, you say, you have to go on this path.
What do you say?
Yeah, that's right. Exactly. If there was only one path here, I'd be fine as long as I didn't allow. It's more that if I have multiple and I restrict you to using only one of them, you're totally right. And in fact, we'll see in practice, most of the solutions put all the traffic on one path. There are just a few node pairs that often in practice take advantage of the need to split. So part of it is a computational problem I have to get through to be able to get the math to work. And part of it is that occasionally there really is a place in the network where you need that flexibility for efficiency reasons. Yeah.
Well, if there is just one edge and just 2 vertices, if there is just one edge, just 2 nodes,
right.
If your functions U and F are sufficiently complicated, you can still have any number of solutions, right? If they're monotonous, but like...
Oh, in terms of the number of paths, you mean?
No.
Sorry,
You just have one path, one edge. But your functions U and F are sufficiently sophisticated.
Yeah, that's fair.
Then it's still pretty bad.
But the nice thing here is my U function is concave and my F function is convex. Because essentially I've got this diminishing return function. Utility increases but diminishes. And for F, you think of it like an MM1Q. It's essentially increasing and convex. And that's what's letting us make that decomposable too. So actually, in fact, what this is fixing is the constraint, right? I had a non-convex constraint that I'm fixing by moving to this flexible splitting over multiple paths. I already had a convex objective function before I started because the U function and the F function have the property that I need to make that true. Now, as you can imagine, if I try to handle other classes of traffic whose utility functions are not as friendly as aggregate throughput is, that might not be true anymore. But for throughput, it is. And for certain delay formulations, like minimizing aggregate delay, that's also true. It's not true for, delay bounds, where you actually have a sharp discontinuity in the curve. So our delay work that was asked about earlier, we actually assume that we're trying to minimize aggregate delay rather than maximizing the percent of traffic that satisfies a delay bound, which actually wouldn't fit in this kind of framework. Okay, so here's our new problem now. So what do we do? So what are the distributed solutions that pop out of the math are going to have this basic flavor to it. The links are computing, the routers have multiple paths. They may be set up in advance, they may be computed dynamically, or they may be set up statically in advance by the network administrator. They're going to monitor the load in their incident links and compute a so-called price that's going to be reflective of the congestion on the link. They're going to either feed that back to the ingress node, which could be a router or a host, or they'll be picked up as the packets flow through the network, similar for folks that are familiar with ATM networks, similar to the RM cell that ATM networks had. And that source, based on all of these prices, is going to update its path rate. So it's going to both change the aggregate rate at which it's sending and the percentage of that traffic it sends on each of the K paths. The network administrator is tuning some parameters that get tuned on a very, very coarse timescale and otherwise can really take the rest of the day off. Okay, so the network's doing most of the work here. Okay. These other parameters, which I've cryptically referred to here, are going to be some tuning parameters that pop out of the math, and they're going to be the bane of our existence. And it's going to be why the so-called optimal protocols are not going to be the final answer to the question. Okay, so what do we do? So I'm not going to go into a lot of detail about exactly the theoretical techniques. I'll just say that the decomposition techniques we use are pretty standard. There's a little bit of work to turn the crank and make them pop out, but we didn't really do any significant innovation there. Just going to try to give you a flavor for what that process looks like. So essentially what we have are prices that are penalties for getting close to violating a constraint, like the capacity constraint on each link. We're going to punish a link that's very, very close to overloading its link. The path rates are going to be updated based on those penalties to shy away from paths that are congested. And so to give you an example of this in a single path setting, think about what TCP congestion control does, which can be expressed in a similar kind of way, just it's a little simpler than the problem that we have. The link prices are things like packet loss or packet end-to-end delay. And the sources are updating, additively increasing or multiplicatively decreasing based on the prices they get back from the network. In the case of TCP, those prices are implicit in the observations the sources themselves make about loss and delay. In our case, they're going to be explicit and provided by the network by marking the packets or by providing feedback to the end host. Okay, so our problem is going to be very similar in spirit. It's just more complicated because our objective has 2 terms in it, rather than just aggregate utility, and we're using multiple paths instead of one. But the basic technique is pretty much the same. And so just to give you an illustration of what kind of transformation we'll make of the problem in order to make it distributed. So one constraint we have, and it's really the main one, is we have to stay below link capacity. Okay, so we're going to do things like this. We're going to say, okay, let's suppose the link load is YL. I want to make sure YL stays below C. And one way I can do that would be to do some sort of subgradient feedback update, where I essentially look at the link load and see how I'm doing. And if I'm in fact at a very high load, I'll actually increase the price, because the gap, if link load is higher than YL, the target load I'm trying to get at, I'll actually increase the price, and that'll make the path that this link traverses, the path that's traversing this link look less attractive, which will ultimately lead the source to send less traffic on it. So here I've already introduced one of these so-called other parameters that I'm going to come back to later. So the step size is going to be something the network operator has to tune. Okay, so that's unfortunate, and we'll see later it actually is, it is problematic in practice as well. But that's the kind of thing we're doing. We're taking each of the constraints, and now you can see this is decomposed in the sense that a link alone can do this computation by itself. So each of the links in the network are doing a simple kind of update like this. And other parts of the problem, other constraints and other parts of our objective function get decomposed in similar ways into things either the edge node is able to do on its own or the links are able to do on their own. Yeah?
Like close to link load by definition.
So in fact, and I didn't go through this here, but you can end up now decomposing, making link load match YL into its own update. It's a made-up variable. So it's made up. It's made up. So another constraint I now have is link load equals YL that I can solve by saying YL minus link load has to be 0. And I can measure how well I'm doing obeying.
YL has no meaning.
It has no real meaning. It's an artificial construction just to allow me to decompose the problem. And it's just one way of decomposing the problem. And in fact, we use 4 different decomposition techniques that vary in terms of which constraint they go after first and in what way they decompose it. But they're all pretty standard ways of taking linear constraints and decomposing them into updates. Okay, so just to give, so essentially another example, so this we call defective capacity, essentially gives us an early warning of impending congestion. We're doing something to get a sense of how much load the link should have. We're noticing that we're doing worse than that, and so we're going to panic a bit by penalizing traffic from using that link. And there's another parameter that allows us to overshoot the actual load on the link, to go a little faster, to send more traffic than the network can handle in order to converge more quickly. And I'm not going to go into that. But essentially, each of the decompositions we do have a very specific physical meaning in helping the links or the sources understand the congestion state that they're in, based on local computations they can do. So skipping some of the details, because again, as I mentioned, my goal here is to convey the journey more than the outcome. Essentially, we end up with 4 different decompositions. We take all the techniques the optimization community has come up with for slicing and dicing these kind of convex optimization problems, and they all have the same flavor. The links update a price. The sources update their splitting rates based on that. And they all just differ in which order they try to address each of the constraints in the problem. And so we end up with 4 different algorithms with different numbers of tuning parameters and different degrees of aggressiveness in responding to congestion. And all of them, so some of them are essentially going to have different dynamics than the others. They're all provably optimal. They're all provably stable. They are, by definition, by the way they were derived, distributed algorithms for solving the optimization problem, where the components doing the computation are the links and the edge nodes. Okay, so that's all well and good. The theory tells us that we're stable and optimal, but we're really not done, because we don't actually know how they perform in practice. Okay, and in fact, practice is going to, in fact, deviate quite a bit from the theory in some cases. So again, we know they're going to converge, but they're only going to converge for diminishing step size. They're only going to converge on some time scale that we can have extremely, extremely weak bounds on, not strong enough bounds for us to be happy that they're going to perform well in practice. And these tunable parameters, beyond telling us that they have to be diminishing with time, which isn't really practical, we have no guidance from the theory on how to tune them. Okay, so we have something that is probably optimal and stable, but still not very useful. So what we did is, because at this point our so-called protocols are really numerical computations, right? They're not even algorithms. They're not even distributed algorithms in any really meaningful sense. They're really just function evaluations that we're doing. So essentially, we went into Matlab and we did a huge multi-factor experiment where we varied every parameter in all of these protocols, and made a ton of graphs to study the rate of convergence and the sensitivity of each protocol to its tuning parameters. So the first thing we looked at was how much do we care about the relative value of the user's utility function. When it's 0, that's all we care about, versus being robust by being a little bit conservative in what we put on the network. So y-axis equal 100 means we've maximized aggregate utility. As it starts to drop off, we're being so conservative that that conservatism is costing the users performance problems. What we find in a lot of our experiments is if we operate at w equals 0, the system is extremely fragile, hard to make stable. But fortunately, we've got a relatively wide band of values at w where we get pretty close to optimal behavior despite and not being exactly optimal. So we can make W equal to half or a sixth or something and still be pretty much in a regime where we're going to be able to nearly maximize user utility, and we'll find we can be much, much more robust by making that trade-off. And these are 3 different network topologies that we studied that on. So that's W, so we have a sense of how to set that. It's topology dependent. It relates a bit to the number of diverse paths in the network. But for the most part, we can still, as long as we're W a half or so, we're not in bad shape. So these are the kind of graphs we looked at for a whole bunch of different protocols. So a protocol might have a particular tunable parameter, like a step size. We'll sweep its value, and we'll look at how long it takes to converge with an epsilon of optimal. And the y-axis is the number of iterations. Think of them as round trip time. How many round trip times do we have to keep iterating and updating before we converge? And so in a graph like this, we would look at it and say, well, we converge to near optimal within a few dozen iterations. That's not bad. And we look at the width of these curves to get a sense of how sensitive it is to our parameters. So if we end up setting the step size over here, we're in big trouble because it's going to take 300 round trip times to converge. So we're reasonably happy that this could be worse. It could be narrower, but it's still not great. If we don't get the value right, we're not going to converge all that quickly. And so we compared all these protocols based on graphs like this. And what we ended up with was seeing that small values of W below sort of a sixth to a half were pretty dangerous, but once you had a larger value of W, things are pretty good. And the schemes that had larger number of tuning parameters really didn't do better. Even if you could find the best tuning parameter to use for them, they didn't really converge much faster than the simpler schemes. As you might expect, schemes that allow a little bit of more aggressive transmission, overshooting occasionally, converge more quickly. And in some sense, doing direct updates from current observations of network conditions was more effective than considering past history. Okay, and so we took away from this that all of the protocols, all 4 of the, well, distributed algorithms, I think is probably more appropriate at this point, had some interesting flavor to them, but they each were somewhat unsatisfying in one respect or another. And so we took away these very basic observations, and we cherry-picked aspects of the computations that each of these algorithms are doing to try to take the direct update rules and the techniques that had fewer tunable parameters, and we construct a new protocol that's simpler. So just to show you what that looks like, essentially what we do on every link is we keep track of the capacity of the link and how much the load is either in excess or underneath that. And we update the loss price, if you will, based on that. So you can think of the loss price as saying, well, if link load is higher than link capacity, I'm going to lose the traffic that's in excess of the link capacity. So logically, you could think of this P price as the fraction of traffic that's going to get lost. And the other price as essentially the increase in queuing delay. This is a f prime, so it's the derivative of that f function that looks like queuing delay. So this is a little bit like the link measuring how much queuing delay has been increasing in the recent past. And each of these are equations that appear in various of the other protocols we derived theoretically, so that's where we got them from. And essentially we accumulate a price along the path by summing those up. And so the source looks at each path in terms of the sum of these loss and delay-based prices. Note that versions of TCP do something kind of similar to this. They just do it implicitly, right? They look at loss and they look at delay. We're not so different in the end in doing that as well, although the details are a little different. Yeah?
How frequently do you do this?
So we do the computation roughly on sort of the round trip time scale. You could do it, so you imagine feeding back stuff in the packets themselves as they're flowing.
Isn't that too frequent?
It could be. I mean, you could choose to do it more slowly. It's just if you want to converge more quickly, when things change, you might choose to do it more quickly.
To the close to the capacity, and your TCP starts to react and throws a lot of packets out. Your link opens up again, right?
Right. So what we have going for us that TCP doesn't is the feedback here is explicit, and so we know immediately what the congestion state of the link is, rather than waiting for packets to get dropped before we know. So we're getting, in some sense, a much earlier warning. In exchange, in fairness, for the overhead of making that information explicitly available. Yeah.
But are you multiplexing many TCPs into this network?
Yeah. Yes, you could think of this sort of flow I as really all flows between a particular ingress-egress pair.
So you are reacting, like Victor said, you have the little TCPs, you're multiplexing, reacting, and you're...
There is no TCP here.
Yeah, but I thought you were multiplexing many flows.
Yeah, but they're not doing TCP.
Okay.
Yeah, they're being told to send at the rate that we're telling them to send at. Yeah. So yeah, that would interact quite in ways that might be hard to predict. But yeah, we're essentially telling. You could think of us as telling the ingress router how to shape the flows that come in, or you could think of it as the ingress router telling, or the ingress router being the host, who's being explicitly told the rate at which he should send. Yeah. And that's actually critical. We get our faster adaptation than TCP because we're being so heavy-handed. Yeah.
Compare this to MPLS's auto bandwidth. How would that compare to that?
So my sense of MPLS auto bandwidth, for folks who don't know, the basic idea on auto bandwidth is if you encounter congestion, you can essentially dynamically set up a new path.
Dynamically grow the bandwidth of an LSP and it'll set up a new path for itself, right?
Yeah, exactly. The main difference here is we're continuously doing updates. You can think of auto bandwidth as a, hold a parachute because things have gotten bad. Here we're going to be continuously adapting the sending rates and splitting ratios over the multiple paths. And we don't have a target capacity for that path at the beginning. We're just essentially always letting the network tell us what to do. So auto bandwidth is conceptually similar, but it's a bit more of a pull the parachute when the plane's blowing up kind of thing. Yeah.
The price is a multi-bit feedback, or is just a...
Prices are what?
Is that a multi-bit feedback, or is
it is. It's a number. It's a number corresponding to the current price. So if you were to think of it in ECN terms, it would be a multi-bit variant of ECN. If you wanted to discretize that and carry it in the packet. Yeah.
On average, how many source destination paths do you have?
Most of our experiments, we had about 3 to 5. And that was primarily because the topologies we were working with were backbone network topologies where you really, between city pairs, would have something in that ballpark. And we thought that was sort of reasonable overhead to put on the Ingress switch. I'm curious in a data center context what would be the right thing to do. I assume that number would be too small to make more effective use of a data center network that has more paths of comparable latency available to them. Okay, so that's roughly what Trump does. And then it does a little local optimization at the Ingress node, which can either be an end host or a switch, to figure out essentially the best way to decide how much traffic to send along those paths, subject to the price of each of those paths, in order to maximize utility, subject to some aggregate price you're willing to pay. Anyway, I'm kind of glossing over details here in the interest of getting through everything, but that's the basic gist. And I should stress again, Trump is not a decomposition. It is not yet another decomposition. It's not pop out of the theory. It popped out of our intuition applied to the experiments, applied to the protocols we got from the theory. We can prove a few things about it. We know under certain conditions that it's stable and optimal, but we can't prove as strong a results as we're able to prove for the 4 other protocols we started with. When we did this massive multi-parameter sweep in Matlab, we found it converged substantially faster, and it has only one parameter that's pretty easy to tune. So we're happy for the trade-off here, even though we don't have as rigorous results from the theory. Okay, so it's still, as you can probably tell from the fact we're evaluating it in Matlab, it's still mostly a numerical experiment. It's not really a simulation. There's just a bunch of equations that we're iterating through with assumptions about traffic being a fluid and about feedback delay being constant, all of which are really not true in practice. So the next thing we do is we translate that into a packet-based protocol. And nothing here will surprise you. This is pretty easy stuff. We're now going to have time intervals t. We're going to count load as the amount of bytes that go across a link during that time period. And we're going to update the link prices every time period. And we're going to define that time period to be the maps of the RTTs of the different paths that are being used. Could do it less often than this. This is something that seemed reasonable to us because you reasonably can't get the feedback from all the paths any quicker than that. We haven't yet understood deeply how much larger we can make it than this and still have the stability properties that we see in the experiments. But with this update rate, we do see stability. Okay, so what does it look like in the end? Oh, I should say also, when a new flow arrives or departs, it knows from the Ingress node what the prices of the paths are, and so its appropriate rate for sending can also be determined directly because we know our current view of the state of the network. Because unlike TCP that does sort of a slow start, we know the appropriate rate that this flow can send out amongst the group of flows it's part of, because we already know what the conditions in the network are. Okay, yeah.
Maximizing utility doesn't really talk about fairness among flows, right?
Yeah. So that's an interesting question. If we were trying to just do so TCP actually does have a notion of fairness when it does that. We don't necessarily inherit that notion of fairness. So we looked empirically at that, and we do see that we tend to do a pretty good job evenly, essentially not starving. But the property that TCP has, where it actually does give a certain fair share, we don't inherit that property because our objective function is different.
No, I know, but what do you end up with? What kind of fairness do you end up with?
It's not actually obvious what we end up with.
I mean, using the log function automatically implicitly gets you some kind of fairness, right? Because if you separate out people too much, the penalty you get for giving somebody more, or the benefit you get for giving somebody more is far less the penalty you give for somebody.
Definitely. So we expect we're doing something reasonable, but because we're also subtracting this F term, we can't be 100% sure what we're getting, but the intuition, especially if we keep W, that sort of weight between user utility and network utility, to be pretty small, the hope is we inherit similar fairness properties to TCP. It's just we can't prove that when we're in the general case. Other questions? Okay, so that's essentially what the protocol looks like. So then we went to NS2 and did more realistic experiments with real delays, with real paths, and with an on-off heavy-tailed traffic model, mimicking sort of what we expect web traffic to look like. And essentially what we want to know is all these multi-factor experiments we did in Matlab to be able to stumble along the right answer to our problem. Were those things misguided because they were such an abstractive view of what the network looks like, or did they give us a reasonably good view? And in fact, we did NS2 experiments for the other protocols to get a sense also of whether our Matlab results were accurate. And actually, they were pretty accurate in practice. So we feel like the Matlab results that we used as sort of a signpost along the way gave us at least some insight of which way to turn at different stages in the work.
The paths between the source and destination, were they approximately equivalent in terms of counts and things?
Relatively. We tended to pick the k-shortest paths where we did, if the k-shortest paths shared so many links in common, we would essentially try to have paths that were a little bit more diverse. So you could think of it as a trade-off between k-shortest paths and k-link disjoint paths, something a little in between that.
If you had paths which were very different, would you still include them in your...
No. I mean, you could, but they're not going to help you much, because in the end, you're probably not going to use them very much. So we chose to limit the number of paths to be sort of in the 3 to 6 range. Again, the protocol would still work, and in fact, would probably work at least as good, if not better, if we included more. It's just that we chose not to include them because we assumed they would end up carrying infinitesimal amount of traffic anyway. And in fact, we found that as we did experiments where we increased the number of paths, once we got above 4, we didn't really see additional benefits from having more.
It wasn't about increasing the number of paths, but actually the diversity between the paths in some sense.
Yeah, there's a trickery to that in the sense that if your k-shortest paths have too many links in common, you don't get enough benefit from the diversity. And yet, if you pick completely disjoint paths, the k paths you pick might have widely varying lengths. And so I think there's some art to picking the paths. And we did some experimentation with that. And certainly, if we just pick only the k-shortest paths, we don't do as well as if we pick kind of a mix of disjointedness and shortness. Don't know what the right answer is there, but I think picking a handful of paths that are not much longer than the shortest path, that have sort of maximal disjointness subject to that, something in that ballpark we think will work well. But that's certainly in the realm of human engineering, not something we can say something rigorous about. So how do we do? So I'm running low on time. Yep.
So just some comment, we also encountered a similar problem in terms of choosing paths. The way we did was the following. Of course, that's an offline algorithm. Suppose I know the traffic matrix, and I could make a problem convex by using the link formulation, not the path formulation. Link formulation was about flow conservation alone, right? So therefore, not implementable. You make a link formulation, you can solve the problem in an optimal way. And then you have a flow. You have flow. What you can do is you can use some kind of maximum coverage.
That's interesting.
And you essentially have a flow model, and now you need to generate paths. For example, the algorithm is called a path coverage algorithm. We have an algorithm.
Oh, that's
and
really
typically it's on order like 5 to 6 for the backbone networks.
Okay.
And you can reach some kind of coverage like a 90%. Then of course, then you can do this for offline, pick 5 to 6 using the path coverage, and go back and now use this algorithm in online.
Oh, very nice.
That will give you both.
Okay, very cute. That's nice. Yeah, that's exactly what we don't have. I mean, we're essentially doing things like multi-commodity flow and then picking the paths that tended to carry traffic, but we weren't really formalizing it quite that much. That's really cool. Yeah. So now I'm just going to really briefly, given I'm low on time, run through just a few graphs. So what you're seeing on the left here is a time series plot of Trump running, and the y-axis is the aggregate throughput. Well, keep in mind here, aggregate throughput includes stuff that's getting lost. So these little spikes you're seeing on the upper left are traffic that's, in fact, looks like it's a good thing, but it's actually bad because traffic is getting dropped on the floor. So what we see at steady state is what load the network is carrying in aggregate. So as you can see, if we make W, this parameter where we are conservative, too high, we end up being so conservative that we hurt the aggregate throughput. But in fact, we can actually do pretty good, even having protocols that are much more stable, by having W just be kind of in the 1/3 to 1/2 range. So that's just sort of a quick confirmation of that. If you look at the graph on the right, that was one of the earlier protocols that we evaluated, optimized with its step size to the best value we could possibly get for it after sweeping Matlab like crazy. And as you can see, the way it behaves under 2 different settings of its step size is it's pretty sensitive. Those 2 step sizes, a little hard to see, are pretty close to one another. The black curve is doing as good as we could possibly do if we let Matlab search for a long time to find exactly the best value. The blue curve is not much different in step size, and yet you can see it, the thing's just going nuts. So again, we have a protocol that's provably stable and optimal, but we have to have the right step size to get it to work. Whereas we found with Trump, actually, it was pretty insensitive to the tuning parameters. We did some experiments with failure. So here we look at 3 different paths that are carrying traffic between a particular ingress-egress pair. The blue, the red, and the green are the loads on the 3 different paths. Actually, what you can see from this, first off, is that the vast majority of the traffic is going on one path. And in fact, this is a recurring thing. In other words, somebody asked earlier, do we really need multiple paths, or do we just need flexible splitting on whatever paths we have? And the latter is the point. And in fact, for the vast majority of source-destination pairs, we do see 100% or nearly 100% of the traffic go on just one of the paths. When we fail a link on the green path, we see the system adjust pretty quickly and to put traffic, more of the traffic now on the third path, the red path. Although less, because now the network has less capacity and is not as able to handle the load. But it responds pretty quickly, and here the time is in seconds based on I think it's the sprint topology, looking at the link between New Jersey and, that Indiana, I think that's Indiana. And finally, we also did some experiments where we varied the average file size. So we looked at the web objects. They have a Pareto or exponential distribution of file sizes, and we changed the mean file size. And we're looking here at a y-axis where 100% is good, where we actually maximize the aggregate throughput. And as you can see, if the file sizes are really tiny, we're not going to do that great. But if the average file size is reasonably big, where we have at least a few round trip times for the flow, we actually get pretty quickly up to a reasonable use of the network. And it's actually fairly robust across a range of different distributions. So the mean seems to be more important here than how heavy the tail actually is. Now, if you were doing TCP, as you might expect, small flows are also extremely problematic for TCP, and in fact are even more problematic than they are for us, largely because we essentially have information about the state of the network when the flow starts. So we're able to jump in right away, but it's still going to take us a little bit of time. The flow has to be around at least for a little while for us to not have such bursty traffic that we don't get to the right place before the flow actually ends. And finally, this gets at a question that's come up in a few guises here already, is how many paths do we need? So this is looking at time on the x-axis, looking at the aggregate throughput depending on how many paths we let the network have. The black curve is where we force everybody to use one path, and blue is 2, yellow is 3, green is 4. So essentially having 3 or 4 paths, we're starting to get extremely diminishing returns at this point by adding more. This is for the, I think the sprint topology, or it's an ISP level topology. Now, again, if you were to look at a topology with greater natural path diversity, you might need more than this. But what we found for the backbone networks is that there were so few paths that were substantially close in latency and number of hops that really the 5th, 4th, and 6th path were so long that you wouldn't really have wanted to put traffic on them anyway. So for the most part, the additional paths don't buy you much in this context.
Is the fact that you have very little path diversity the reason why you're getting integer results when solving a linear program?
That's a great question. That could very well be. I don't know.
I mean, just as an experiment, if you had like a fully connected graph, it would be good to see if you're getting.
Yeah, that's a really good point. Yeah, although even when we have 4 paths, we really tended to see 100% rather than splitting.
No, but are they 4 disjoint paths?
So they're largely disjoint, not completely.
Because if the 2 split flows are interacting at any given point, then it might just say that, oh, I'm just better off just sending everything on one path. It would be good if it's completely disjoint. So.
Yeah, that's a really good point. Yeah, so we didn't do that, but that's a really good point. So anyway, to conclude, Trump in the end has one easy-to-tune parameter that only needs to be tuned when this W value is set really small, which we tend not to want to do anyway because it makes the system not terribly robust. It's pretty quick in recovering to link failures and recoveries. And it seems to perform in a way that, although it depends on file size, is not terribly dependent on the variance of file sizes. And we call it Trump because it trumps the other algorithms. We had an earlier protocol I didn't subject you to called dump. Anyway, we dumped dump because Trump dump. Anyway, Trump is better than dump. And we think, although we don't know for sure, this is something we're still working on, that it might be possible to design a variant of Trump that works with implicit feedback. Note here, we are passing back prices on the links with information that kind of maps to loss and delay variation. We think that intuition could be applied to have a variant of Trump that works with the end host or edge router implicitly inferring the loss and delay variation, but we haven't yet gotten traction on that problem. So another question you might have is, okay, so far I've still been pretty abstract. Yeah.
How many bits are you sending back?
think we're just representing them as floating point numbers. Yeah, it's a good question, though. What level of granularity do we really need? I suspect a handful of bits is probably enough, but we definitely need more than one.
Because, I mean, sort of this, like you said, with TCP you can sort of reverse engineer and get the same thing, but usually there's like a differential equation model of TCP, and they assume like many flows, so each TCP source is its own changing still little. And something I was always wondering is there any sense as how much mixing you need to actually be able to have that model represent anything?
Yeah, that's a really good question. Yeah, I don't know if anything we do here sheds light on that, but it's a good question. And we definitely are taking advantage of some of the dynamic range of the price information here too. So it'd be interesting to know if we represented it logarithmically, how many bits would we really need to do it. I suspect that we'd need a handful, but hopefully not a huge number. So one thing you might be wondering is, what are these components? I've talked pretty abstractly about the edge and the link and so on. And so what is the new architecture, if you will? So if we look at the picture I had at the beginning of the talk, the operators are tuning link weights and setting penalty functions and such. Under Trump, they're at most on a very coarse timescale computing the paths on behalf of the routers, if we don't want the routers to do that themselves. And they're tuning some offline tunable parameters. So they're not doing very much. The sources in today's TCP are adapting their sending rate. Here we're adapting the actual rate on each path. And today's routers are doing some form of shortest path routing. Here they're not doing anything except computing prices on the links and feeding them back to the sources so that the sources can appropriately split the traffic over multiple paths. And so something I've talked about with a number of people in this room is whether, in fact, this would allow the routers to operate without a control plane. Right? Particularly, you see the things that are in parentheses here. Who's doing this? The multiple paths can be set up by the routers or by the management system. The prices can be computed by SNMP polling of the link loads or by the routers themselves. And so really what's nice here is you can actually vary quite a bit what is actually done by the routers. And in fact, could even imagine an implementation of Trump where the routers do almost nothing, except collect the measurement data about link load on some sort of round-trip timescale. Okay, so I started off by saying the math was going to give us an architecture at the end, and that was a little bit optimistic. So what we end up with is a division of functionality, but exactly what is the source and what is a router is still left a bit open. So the sources here could be the end host, could be the edge router, or even could be a mix of the two, where maybe the end host is computing or enforcing an aggregate throughput, and the edge routers are doing the splitting over the multiple paths. So that you could imagine an end host variant of this, which might be appropriate in a data center network. You can imagine an edge router variant of this that might be more appropriate in an ISP. The feedback in everything we've assumed so far is explicit about the link loads and the prices that are computed based on them, but we suspect, we're not 100% sure yet, that an implicit version might be feasible. And of course, that would be real nice if we wanted an interdomain version of Trump, right? Because right now we're relying on quite a lot of cooperation from the network elements that would be extremely problematic in an interdomain setting. And finally, the computation of the paths, of the prices, of the path rates could be done at the links and the sources, or could be done by the management system itself and pushed down into the network elements and collected up from the network elements if one wanted to do. So in fact, the network management system could implement almost this entire scheme just by monitoring link load and pushing down sending rates down to the end nodes, or be not involved at all if you put all that function in the routers. And we view that as a plus that in fact those questions are left open, because the actual choice between these things might be driven by completely different issues, like trust and security issues about whether you trust the host or you trust the routers. Maybe if you're Microsoft, you trust the host, and if you're AT&T, you might trust the routers. And so you both have a variant of Trump that might make sense depending on who you are.
Completely left open, because when I asked you the question, you actually said not TCP, so you were thinking edge routers, and then you said explicit. So in your mind, it's not completely open though. Yes
and no. You're right at some level, but you could imagine what the edge router is doing is shaping at the sending rate, in which case the host could send at whatever rate it wants, but it's going to get rate limited as soon as it tries to exceed the shaper. In which case you could either say, well, it should rewrite its code so it doesn't hurt itself by exceeding it only to have its packets dropped, or you could also look at how well would somebody implementing TCP do subject to a rate limit that's been computed by the network. We haven't studied that, but one could do that. It would just be clumsy, I think, to do it that way, but it's certainly feasible to do it. Yeah.
I think it'd be really helpful to compare this to RSVPT and auto bandwidth with MPLS, because I'm wondering if the utility of going out and having to pull the device and pull in stats into a measurement system is pretty much equivalent to that function.
Oh, that's a really good idea.
So
yeah.
it might be a very interesting adjunct.
Yeah, that's a great idea. And certainly MPLS could be used here for the multipath establishment. And we've looked at the splitting ratio business can also be done using existing MPLS features as well. But we haven't done the rest of the comparison you mentioned. So I'll just conclude by saying we've been looking at implicit feedback-based extensions to Trump, and in particular we're interested in that because if we wanted to do this in an interdomain setting, we consider the reliance on explicit feedback a non-starter there. So we want to try to resolve that. And I'll just end by touching on a question that came up at the very beginning of the talk, and excuse me for running over. I talked purely about throughput here. But you could imagine applications that would prefer a utility function that captured delay. And so we've gone through this exact same exercise for delay and have a different protocol that is structurally very similar, multipath, feedback of prices, and adaptations of splitting ratios for traffic that's inelastic traffic that's delay sensitive. And a similar kind of thing, we can actually find the provably optimal stable blah, 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 and a variant of it that's practical. So pretty much the same story, just with a different utility function. Now, what if you have both in your network? You have both delay sensitive and throughput sensitive traffic. Well, then essentially your objective is a weighted sum of the two objectives in these two earlier studies. And what's actually really an interesting gift from optimization theory is that optimization problem can be decomposed into two optimization problems that are largely independent, that correspond to the two protocols that we just derived up here. So essentially, that optimization problem tells us that the right thing to do is to run the optimal protocol for each of the two classes and have an adaptive splitting ratio for each link to use in allocating bandwidth to those two different classes of traffic. And so this, we think, is an interesting framework for what we call adaptive network virtualization, where the network is running two customized protocols in parallel, but is dynamically adapting what share of the bandwidth each link gives to those two classes of traffic to maximize their aggregate utility at the end. And so we think in general this body of techniques that Mung and Stephen and Frank have been doing over the years is really quite exciting. It really provides a way for us to think much more methodically about doing network protocol design. And although there's certainly a place for engineering judgment and human intuition, the theory at least points us in the right way so that we hopefully make better decisions. And I'm sorry for running over. I'd be happy to take questions if I'm not already over too long. Thanks. If you need to leave, feel free to